For the first talk this afternoon, we have Inbar Klang, who's going to tell us about spherical scissors congruence K-theory.
Thank you, and thank you for the Hagoromo talk as well. Yeah, and thanks to the organizers for organizing this workshop and for having me speak here. I'm going to talk about something that, as far as I know, is not related to the telescope conjecture. But you know, a lot of you care about algebraic K-theory of ring spectra, and we do have an algebraic K-theory type of spectrum showing up here, so hopefully that is something that people can relate to. So I'm going to talk about spherical scissors congruence K-theory, and this is joint work with Josephine Kuiper, Carrie Malkovich, David Murley, and Thora Wittek. And so I'll start by just saying a few words about what scissors congruence is. So basically, scissors congruence is when you cut up polytopes into pieces and then assemble those pieces back together. So in this example, I'm going to need you to pretend that this is a square and that this is a right-angled triangle whose sides are equal to each other. And that is what I've roughly tried to draw here, but you know, when I don't have my iPad and Notability to keep me aligned, it doesn't always work that well. So the way we can see that these two things are scissors congruent is we can cut this up into these two triangles and then assemble these two triangles into this square. And you know, if I were being precise about area, you know, like that these two triangles precisely assemble into these squares, and these two are scissors congruent. All right, so let's just also give a precise definition. Oh, I should ask, is this size of writing fine? Does this work for the people in the back of the room as well? Great, thank you. Okay, so here's a definition. Polytopes P and Q are scissors congruent and I will abbreviate that as SC. If P is the disjoint union of some, or not disjoint, but union of some finite number of polytopes Pi, Q is a union of the same number of polytopes Qi. These Pi's and these Qi's are isometric for all I. And this union is basically disjoint, so the measure of the intersections is 0 if I is not equal to j. So that's what's going on here. We have our P1 and P2 and our Q1 and Q2. All right, so here's a remark about the various contexts in which we can do this. So, so you can talk about scissors congruence in any dimension. Let's call it n. And also in different geometries. So the most familiar one being Euclidean geometry. So I'll call n-dimensional Euclidean space En. spherical geometry, Sn, and also hyperbolic geometry, Hn. So you can talk about polytopes and isometries and scissors congruences in all of those geometry. So here are some examples. Once we have some kind of notion, we want, and oh, this board is not erased. Okay, sorry, I thought I got that one. This is not my hidden picture. Like, surprise, symptomic cohomology. Okay. So here's some low-dimensional examples. So if you have polytopes in one-dimensional Euclidean space, they are scissors congruent if and only if their lengths are the same. Great. Continuing this trend, if you have polytopes in two-dimensional Euclidean space, those are scissors congruent if and only if their areas are the same. And there's various proofs of this, but essentially you can always cut off triangles from your polytope and assemble it into a rectangle that's 1 by area. And so that is sort of how that goes. And given that that's so like constructive and concrete, it is also then reasonable to ask this question, which Hilbert asked in the early 1900s. So this is Hilbert's third problem. So for polytopes P and Q in three-dimensional Euclidean space, does their volumes being equal imply that they're scissors congruence? And the answer actually came pretty quickly, about a year afterwards. And the answer to that is no. So two polytopes that are scissors congruence will always have the same volume. Volume is a scissors congruence invariant. But the other implication is not true. So Dane came up with another invariant. And with that, he showed that the cube and a regular tetrahedron of the same volume are not scissors congruent. So what happens here is that they are distinguished by another scissors congruence invariant that's called the Dane invariant. So I'm going to tell you what that is, because sort of generalizations of the Dane invariant are at the heart of what we're doing here. So the Dane invariant of a three-dimensional polytope is the sum over edges in this three-dimensional polytope of the length tensor with the dihedral angle of that edge. And this is in R tensor R mod pi times the integers. And so here L is length, and theta is the dihedral angle. So the dihedral angle, this means that this is the angle between the planes of the polyhedron that meet at the edge E. So I have prepared a picture in advance for this because I do not trust myself to draw a tetrahedron in real time. Okay, so here's a tetrahedron. If I'm looking at this edge E, I have the two triangles that meet at that edge, and the angle between them is the dihedral angle at E. So here, at the risk of revealing my next picture, this is the edge E. And the dihedral angle is the angle between those planes. Okay. So one thing that's interesting about this invariant is that it was constructed before the tensor product of abelian groups. So Dane somehow phrased all of this without actually knowing what the tensor product is. But you know, you can all imagine things about like, oh, you're allowed to, like, whatever you multiply by here, you're allowed to move it over here type of thing. So anyway, so this is another scissors congruence invariant. And that distinguishes between the cube and the regular tetrahedron in 3 dimensions. All right. So then, you know, we want to talk explicitly about where these scissors congruence classes of polytopes live, and they live in scissors congruence groups. So let's let Xn be an n-dimensional geometry. And by that I mean Euclidean, spherical, or hyperbolic. So the scissors congruence group of X is this free abelian group on polytopes modulo scissors congruence, basically. So there's a thing where we mod out by isometries. And there's a thing that breaks the polytopes up into pieces. P is equal to the sum of the PIs if, well, same thing over there. So P is the almost disjoint union of these PIs. Where they intersect at measure 0. And one variation which will be really important for us is something that is special to spherical geometry, where you can also take a reduced version of this. So in spherical geometry, you can also reduce. So P tilde of Sn is P of Sn modulo suspensions of lower dimensional polytopes. So SQ is 0 for polytopes Q in Sn minus 1. And that's the second picture that I drew for today of Q and SQ. So here, this is an example of a trivial element of reduced scissors congruence K-theory of S2. So what we have here is we have this polytope Q inside of S1. So it's just a segment of the circle. And we're suspending it. So that's the polytope SQ. And these are the kinds of elements that we're modding out by in the reduced spherical scissors congruence groups. Okay, and one reason why these reduced groups end up being important is the following observation. So the Dane invariant, where was it? The Dane invariant over here is actually a group homomorphism. That goes from P of E3 to P of E1 tensor P tilde of S1. So one way in which these reduced scissors congruence K-theory groups are important is that that's where these angles live. So when I talk about length tensor dihedral angle, length is going to be in P of E1, and the dihedral angle is going to be in reduced spherical scissors congruence K-theory of S1.
Definition of key of Xn. Are the keys like what dimension are the keys?
The n-dimensional.
N?
N-dimensional polytopes, yes.
Okay.
Yeah, thanks.
For these reduced groups, is it possible to put them together into a graded ring?
Oh, absolutely. Yeah. So, So this is a prophecy about the next thing that I'm going to write on the board, which is that this is actually a lot more structured. There's a lot more structure here. So this is a theorem of Sa from around 1980, which says that the sum of all of these reduced spherical scissors congruence K-theory groups, this is a commutative Hopf algebra. And because we'll refer to it again, I'm going to call this the Sa algebra. And furthermore, this is a co-module structure. So the sum over n of the scissors congruence groups of an n-dimensional geometry is a co-module over it for any geometry X. So spherical, Euclidean, or hyperbolic. So this is great news because we love more structure. Having a commutative Hopf algebra is much better than just having a group. So just to remind you, commutative Hopf algebra, this means that we have a commutative multiplication. We have a co-associative co-multiplication. Those are compatible in the way that you would like. And you also have an antipode that is an anti-involution type of thing. Is this the last thing I wrote? Yes.
You're saying it's not co-commutative?
No. So I don't think this is in Sa's work. In our paper, we do show that it's not co-commutative. Yeah.
So I guess this gives you some generalization of the Dane invariance for EN.
Yeah. So there's all these higher Dane invariants from sort of En to En minus k tensor reduced spherical scissors congruence of Sk minus 1. Yeah.
Is it expected then that will distinguish scissors congruence?
So that is a conjecture. That's called I think that's the generalized Hilbert's third problem, which conjectures that if you do actually put all of those generalized Dane invariants together, so all of the homomorphisms that you get from this co-module structure, that does give you a complete invariant for scissors congruence. It's not known generally. So for example, like it's known generally, I think, just for dimensions 3 and 4. I think dimension 5 is still open. So it is very difficult, but there's a lot of work studying sort of like the kernel of the Dane invariant and trying to say various things about it. Yeah. All right. Other questions before we move on to the higher K groups? Okay.
What are the operations in this Hopf algebra?
Like where the multiplication of the
Big O multiplication.
Yeah. So maybe I'll say like the multiplication comes from sort of product of polytopes type of thing. The co-multiplication comes from some generalization of the Dane invariant. So basically, like you take a simplex or some kind of sub-polytope, and you take its link. And so basically, you're taking like simplex tensor its link would be the co-multiplication. So that's the kind of thing that's going on there. Yeah, yeah. It's all very geometric. Like it's all like you can actually draw pictures of what these things are doing. All right, so let's talk a little bit about the higher scissors congruence K groups. So here's some intuition for why scissors congruence is even a higher K groups type of situation. So the intuition is that a scissors congruence group is pi 0 of some space of polytopes in X and scissors congruences between them. So when we're modding out by the relation of scissors congruence, it's like we're modding out, identifying points whenever they have a path between them. Same kind of thing. And so another thing that you can notice about these scissors congruence K groups is that this P of xn kind of looks like a K0. So if you look at the definition, we have like, oh, this is telling us when a bigger thing splits as a sum of smaller things. That's very much a K0 type of description. And so this then prompted Vrije to find the higher algebraic K-theory description of scissors congruence. So she proved that these scissors congruence groups are pi 0 of a K-theory spectrum. So you can think of this K-theory spectrum as, scissors congruence group is pi 0 of some space. Fortunately for us, this space ends up being an infinite loop space, and so we can deloop it into a spectrum. And so that's the scissors congruence K-theory spectrum. So let's denote the spectrum K of this category called PXIX. And so here, I of xn, this is the group of isometries. So, for example, I of Sn minus 1 is the orthogonal invention with a discrete topology, but we'll say more about that later. So scissors congruence K-theory is pi 0 of some K-theory spectrum, which is great. And maybe I'll also say for our purposes, reduced spherical scissors congruence K-theory is also pi 0 of a reduced K-theory spectrum. So let's call that K tilde of P Sn minus 1 O n. Okay, so I told you about this commutative Hopf algebra structure on this sum of the reduced scissors congruence K-theory groups. And so our main theorem so these are our initials. Fun fact, our group chat is called Kitty Cat Meow. So that is, I think that is the name of our acronym now. Feel free to use it. So the main theorem that we proved is that if you take the wedge of all of these reduced spherical scissors congruence K-theory spectra, this is a commutative Hopf algebra spectrum. And its pi 0 is isomorphic to the SA algebra as Hopf algebras. Okay, so this is lifting this theorem of SA to the spectrum level. So in the remaining part of the talk, I want to say a little bit about how we approached the proof of this theorem and also what the challenges are that came up.
When you say a commutative Hopf algebra, is that highly structured, like E infinity, or just?
So the multiplication is E infinity, and the co-multiplication is E1. Yeah. So it's not just in the homotopy category. Yeah. So here is the approach, and here are the challenges. So one of the important tools that we use to build this structure is this really cool theorem that Carey proved, which says that scissors congruence K-theory is a Thom spectrum. And not only that, the description is even nicer in the case of reduced spherical scissors congruence K-theory. So specifically, if I look at the reduced spherical scissors congruence K-theory of Sn minus 1, this is equivalent to some desuspension spectrum that I will soon describe the terms of. So we're suspending by minus Rn, and then we have a suspension, an unreduced suspension, a Teets building, and homotopy orbits. So don't worry, I'm gonna say what all these terms are. Okay, so
What you're erasing right now,
yes.
is what does the SQ mean?
Sorry, where?
And above what you're erasing? This is what you're erasing.
It's a picture.
Oh, gotcha. Okay, thanks.
Okay, well, I think the question was answered. I didn't quite understand what was happening, but let me know if you have further questions. Oh yeah, yeah, suspension of a polytope. Yeah. Yeah, so, yeah, picture. Anyway, I caught on. It took me a few seconds.
In the case of the spherical case, the reduced K-theory spectrum, is it only changing K0? Or is it also?
No, not exactly. No. So you can imagine that instead of this desuspension, you might have like a Tom spectrum type of thing where you're desuspending by maybe the tangent bundle of Sn or something like that. It's slightly different. Yeah. Okay, so let me explain the terms that show up in this theorem. So here, this ON delta, this is ON with the discrete topology. This is very unfortunate but unavoidable. This T of Rn, this is the Tietz building. So this is the geometric realization of the poset of vector subspaces that strictly contain 0 and are strictly contained in Rn. So this is some highly studied simplicial complex. S is unreduced suspension. Sigma is reduced suspension. And this sigma minus Rn, this is desuspension. And the reason that I wrote it as sigma minus Rn and not just sigma minus n is because I want to emphasize that this orthogonal group is acting on Rn. So the orthogonal group with the discrete topology is here acting on Rn by the usual action.
Also, in the Tietz building, are you considering that as kind of being all discrete as well?
Yeah, so we're not considering the subspaces as being close to each other as far as I can tell. Yeah.
Where is it that this goes from being a space to being a spectrum?
The desuspension. Yeah, so again, for other geometries, for unreduced spherical scissors congruence K-theory, you'll have maybe more complicated things than desuspension showing up. Specifically, you'll have a Tom spectrum. But here, it's really nice because you are really just getting like a desuspension of a space. Well, and then you're taking homotopy orbits, but that's, yeah, it's really nice because you can really do most of the work in spaces. Yeah. So before I talk about sort of the approach to proving that this thing assembles into a Hopf algebra, I want to talk about sort of the convenient model that we have for a part of this. So our convenient model for the suspension STRN. One of the reasons that I wrote it that way rather than just saying like suspension 2 minus Rn something something is because we really like this model and it has helped us a lot. our model for this is we're taking actually the poset of vector subspaces in Rn that could be either 0 or Rn, no restriction. And then we're modding out by some subposets. So realization of the poset of things that are strictly contained in Rn, and also the poset of things that strictly contain 0. So this is a convenient model for this twofold suspension, and this is where we sort of start creating the algebraic structure really explicitly. So once we have this description, our goals are to leverage the direct sum of vector spaces into some kind of commutative multiplication on what we call the spectral SA algebra. So that is this wedge sigma, let's see, sigma minus Rn, sigma ST Rn, homotopy On with discrete topology orbits. So we really, based on the identification between polytopes and vector subspaces here, we really know that direct sum of vector spaces should be giving us our commutative multiplication. And of course, also leverage the Dane invariant into a co-associative co-multiplication on S. And there arise the challenges. Okay, so as always, coherence issues. Maybe let's say something more specific. So one more specific thing that happens is these homotopy orbits that we have, and the fact that different ends are showing up, and we sort of want to somehow put all of those homotopy orbits of all those ONs together. And also, co-algebras and spectra are weird. So more specifically, there's this theorem of Baru and Shipley that says that if you have a strictly co-associative co-algebra in one of our symmetric model categories of spectra, it has to be co-commutative. And like most of those are like suspension spectra, basically. And we know that we're not a suspension spectrum, we're not co-commutative, none of those things are happening here, so we cannot be getting a strictly co-associative thing. Like that's just not gonna happen. We're gonna have to give up on that and go for something that's maybe co-E1. Yes, so those are some challenges that we were faced with. And the trick for dealing with this, this was suggested to us by Sander Coopers, is to use a functor category and day convolution. So for those of you familiar with some of the symmetric monoidal model categories of spectra, this is a really useful trick. So here's the functor category that we use. This category is called DIP for finite dimensional inner product spaces, but also named after Carrie's cat, Dip. This has objects, finite dimensional, real inner product spaces. And morphisms, linear isomorphisms that preserve the inner product. So here are a couple of important things about this category. So first thing is, if we take the morphisms here from Rn to itself, we get On with the discrete topology. So that's great. That's our frenemy, On with the discrete topology. That's showing up over there. Another really cool thing about this category is that direct sum of vector spaces makes it into a symmetric monoidal category. And the third thing is the day convolution. So if C with product that I'll denote smash is, let's say, a co-complete symmetric monoidal category, then the category of functors from dip to C is symmetric monoidal under day convolution. So just to remind you how that goes, if we have two functors f and f prime from dip to C, we use them to map from dip times dip to C times C. We then have this match product on C. So then we have a functor from dip times dip to C. We also have the symmetric monoidal structure on dip. given by direct sum. And we can take the left con extension of this diagram. And this is what we denote F box smash F prime. Okay, so this is some left con extension, but also very concretely you can write down what this is. So if my C is spectra or pointed topological spaces, which are the main cases that we consider, F box smash F prime of V is this wedge over vector subspaces of F of U smash F prime of the orthogonal complement of U inside of V. So very, very concrete, down-to-earth description of this symmetric monoidal structure. Okay, so then once we have this functor category, this is the strategy that we follow. So first of all, we define an E infinity E1 bialgebra structure on what we call the spectral SAW functor. So this is, we denote this curly SF from dip to spectra. And curly SF of V is defined to be suspension minus V sigma ST of V, whose convenient description I have unfortunately just erased. But okay, so we define a commutative multiplication and an E1 co-multiplication on this functor with respect to the Day convolution symmetric monoidal structure. Okay, this is not quite what we want, so then we transfer this structure to our actual spectral SAW algebra, S, which fortunately is equivalent to the homotopy colimit of this spectral SAW functor. And just as, you know, an addendum, bialgebra, not necessarily Hopf algebra, you still want an antipode, and so we also show that the shear map is an equivalence, which gives an antipode. So maybe just to complete this part 3, I'll just tell you what the shear map is. So if you have a bialgebra structure on S, you can use the co-multiplication and the identity to go from 2 smash copies of S to 3 smash copies of S. And then you can use the identity smash with the multiplication to go to S smash S. And there's some very nice results that tell you that if you have a bialgebra for which the shear map is an equivalence, then it's a Hopf algebra. So for a bialgebra, being a Hopf algebra is more of a property than a structure. Okay, so that's the strategy for proving the theorem. It all works out. It takes around 50 pages. So this does work. This gives us a Hopf algebra structure. And so before I finish, I'll just mention a couple of sort of future plans that stem from this. So at the beginning of the talk, I mentioned not only the Hopf algebra structure on the SA algebra, but also a co-module structure. So we want a spectral SA co-module structure on the the various scissors congruence K theories. So here, X is Euclidean, spherical, or hyperbolic. And also, one of the things that's nice about more structure is that it allows you to know more about your spectra. So we want to produce new non-trivial elements in higher scissors congruence K groups. So that's the plan, and yeah, I think I'll stop here. Thank you.
Questions?
Yeah.
So what happens if you view dip as a topological category?
If you use dip as a topological category, then you're not going to get ON with the discrete topology. You're going to get it with the continuous topology, which is a much, much nicer thing, but it's not the thing that we want. So, I mean, all of these calculations, sort of, if you're looking at those sigma ST of V spectra and their homotopy orbits, those are all much easier to study if you take orthogonal groups with a continuous topology, but then they're just not related to scissors congruence K theory. So, like, one of the nice things about K theory is that it has a trace map to something more algebraic. In the case of scissors congruence K theory, that trace map is to group homology of various groups with a discrete topology. And that's really hard. So that's another reason why, it requires a lot of sort of methods to study scissors congruence K theory, because it's hard. Yeah.
So you did all this over the reals, but I mean, you could also have done it with the field Z mod P, right? If you do it with the field Z mod P, then it kind of all connects up with a bunch of classical stuff about the Steinberg module and something.
Yeah, I mean, so I don't know of any work about this, but I do know that some people have been sort of speculating about what happens if you put other like finite fields there or rings like the integers there instead of R. I mean, it's like those are things that you can study and they are related to like homology of arithmetic groups and things like that. but I don't know like what the scissors congruence interpretation of it is. So, I mean, I know, yeah, I talked to some people about a year ago that were thinking of this, and I don't know if it has gone anywhere in the meantime, but it would be interesting to sort of have this link between homology of arithmetic groups versus like polytopes and scissors congruence.
Hi, so if you have a co-commutative Hopf algebra, you can produce a D algebra out of it by taking...
So this is not co-commutative, this is...
Yeah, but here you can get co-algebra E.
Oh, I see.
By taking
Because it's commutative, yeah.
So do you know what you get?
No, I have no idea. No. Yeah, I don't know.
What's known about the higher K groups? Is there any idea of what it might be seeing? Yeah.
So there's not a lot known about them. I think some of the main computations that I've seen are in Carey's paper about this Tom spectrum description. So in that paper, he manages to compute some K1s. And I think once you get to K2, this begins to have to do with like homology of O2 with the discrete topology, and that's really, really hard. And so I think sort of once you get past K1, things get really difficult. So not a lot is known about those higher K groups.
Is it known in particular if they're divisible?
No, I don't think. I mean, let's see. So you end up getting a lot of like uncountable things. I think at least like, don't quote me on this, but the ones that we do know, I think end up being divisible, just because it's a bunch of like R with the discrete topology and stuff like that. But yeah, I don't know in general.
Any more questions?
Yeah, there's one here.
Oh.
So you talked about, how this is something that can be studied for these different geometries, EN, HN, SN.
Mm-hmm.
I'm curious if people have looked at it if there's some more generalized notion of geometry, or people have looked at this, whether it's like some specific kinds of like Riemannian manifolds or some kind of synthetic geometry or something.
I don't know. That would be interesting. I'm not aware of things sort of in that direction, but yeah, I think that could be interesting as well. Yeah.
Not a naive question, but I mean, so why don't we just consider bounded polytopes in Rn, like for for the computation? So what if we just consider the bounded polytopes in Rn?
Sorry, I'm not sure what you mean. So.
No, I'm saying that like if we consider just bounded polytopes in Rn,
Mm-hmm.
right? So and from that also like we'll get some sort of I don't know, some sort of a Grothendieck group we'll get if we are just considering bounded polytopes. And from those from those computations, can we get information about these scissors congruence groups?
Yeah, I mean, so that is a little bit of what's going on here. I mean, you do have some kind of Grothendieck group-ish description, right? You're taking polytopes, you have a sum of polytopes that's given by disjoint union, and you're sort of taking, you're taking some equivalence relation, you're taking some group completion type of thing. So that is the K0 that's showing up in scissors congruence K theory. And those K0 groups are also hard. So like, you know them in dimension 1 and 2, you know complete invariance in Euclidean geometry, I think in spherical in dimension 3 and 4, but once you go up to higher dimensions, yeah, things just become much harder. So even this Grothendieck group type of thing is not easy at all, yeah.
All right, let's thank Inbar again.